Hello everyone, we are Group 41 and today we will be presenting an exciting topic in the field of video representation learning. The title of our presentation is When the Future Become Past, Temporal Timing Temporal Correspondence for Self-Supervised Video Representation Learning. In this presentation, we will explore a state-of-the-art model that enhances how computers learn from videos without any human-provided labels. Specifically, we will dive into the temporal correspondence for video representation learning, a groundbreaking technique that addressed key challenges in this field. Let's get started. Video representation learning is a field of artificial intelligence where models are trained to understand and analyze videos. Unlike traditional image learning, which focuses on static scenes, video learning must also account for the dynamic nature of visual content, how objects move, interact, and evolve over time. This added complexity makes video understanding significantly more challenging than image based tasks. Our prominent approach that has inspired recent advances in video learning is masked image modeling. In masked image modeling, models learn by predicting or reconstructing masked or hidden patches of an image using visible parts. But this form of self supervised learning encourages the model to develop a strong understanding of spatial structures and semantic relationship within the images. When this concept is extended to video domain, it becomes masked video modeling. In masked video modeling, it requires the model not only to reconstruct missing patches within individual frame, but also to infer and model temporal dynamics, how information changes across a sequence of frame. This added temporal dimension introduces new layers of complexity and demands more advanced strategies for learning. Hence, this raises two critical questions. How should we select frames so the model can learn effectively? And second is, how can we ensure the model learns effectively without wasting computational resources? These are the questions the authors aim to address in this work by proposing novel masking strategies, optimized temporal sampling techniques, and architectural modification that improve learning efficiency.
I'm going to discuss after the Moody. Now I'm going to discuss in this slide the major problem. In this video, represents learning uncertainty in the temporal sampling. This problem occur because the video are sequence of frame, but existing methods often rely on the selecting frame for training, but this randomness level to lead to several issues. The first issue is the model loses temporal context, meaning it cannot understand the how object move or change between frame. And second is the causage confusion, especially when the model is forced to predict missing part without knowing the complete sequence. And third is the training become unstable, because the model may learn different each time depending on the which random frame it see. And fourth issue is the finally the model lack consistency, making it unreliable for the tasks that depend on the temporal understanding, like action recognition. And now I'm going to slide number 5. In this slide number 5, I'm going to discuss second major problem, insufficient information compression. What is the meaning in this problem? Existing because not existing method focus on reconstruction makes frame at fixed level, while this seem precise, it seems several issue. First, I'm going to discuss about first issue. The model overfit to low level details such as the color, age, and texture rather than the understanding the high level concept. And second issue, this lead high computational cost, making this model slower to train and run. And second issue, the model ability to generalize suffering because memorization teeny details rather than learning the general pattern. And fourth issue, the it a struggle with temporal understanding, because it is busy focusing on the unnecessary visual information instead of learning how object move. Now next slide, hand over to Parveen.
Uncertainty in temporal sampling, and second is inefficient information compression. Now let's explore the key approaches researchers have used to tackle these challenges. I'll begin with contrastive learning, one of the most widely used strategy in self-supervised video representation. Okay. So first, what is contrastive learning? So it's a cool way for models to comparing video frames, imaging the model saying, "Hey, these two frames are similar and they are opposite," like that. And the main goal of contrastive learning is to model to predict that this frame are similar means positive and these frames are negative means they are further apart. Okay, so the following are key characteristics of the contrastive learning. First is positive and negative pairs. A model learns by understanding what makes frames similar or different. Second is global understanding, focuses on high level semantic understanding, and third is reduced need for labels. So in contrastive learning, there is no need for label data because the model creates pairs automatically. For these popular models like SimCLR, Moco, and Dino, and others. So this is the SimCLR architecture, uh, in which the image is given and the image will be augmented to create different images, and then given to encoder, then given to hidden layers and dense and ReLU layer, and then finally model find the similarity. Okay. So next slide is masked model. This is the second approach. Okay. So masked modeling is inspired by masked image modeling for images extended to videos as masked video modeling. Model in this method, model learns by reconstructing masked part of images and video frames. So there are two main types of masked modeling. The first is pixel space method. In this method, the model tries to predict the exact pixel value of the hidden parts. Think of it like filling in the blanks of video frames, pixel by pixel. Example including MAE, video MAE, drop MAE, and other. Second is latent space method. Instead of pixels, the model predicts higher level features like what an object is or how it's moving. So this is more efficient and includes methods like Dino, V2, iBot, T-Core. So T-Core is the method proposed by the authors of this paper. So mainly we are focusing on T-core method. The key characteristic of marked modeling are local understanding, focusing on learning details in the marked region, higher computation cost. So because of the pixel-based learning, the computation will be increasing. And third is flexibility, works with images and videos by masking and restoring. Okay, so next slide. Existing approach masked modeling. Why masked modeling matters? Okay, so masked modeling lets model learn on their own without any label data. That's a huge because it's a huge because labeling videos in time consuming and expensive. It strikes a balance. Pixel based method are great for picking up local details like the shape of the object, while latent space method focus on bigger concept like what the object is doing. So the flexibility makes it super powerful for the both images and videos, helping models understand everything from tiny textures to overall actions. Plus, it's computationally intensive for pixel method, but latent space method like T-core method make things more efficient, which we will see in later slides. Okay, so this is the architecture. So pixel wise method for AMA, where the video is the input, where in the next step the frames of the videos will be separating and creating masking and encoder and feeding to the model for the further process to decode. um, the latent space method like decode the architecture shift to higher level features instead of reconstructing pixel. The model masked pages and encoded them into a latent space without vision transformer. Okay, so far we have seen the strength and limitation of the both contrastive learning and masked modeling. Uh, okay, so this is it more from my side. Next slide will present my other friends. Okay.
Hello everyone, my name is Siddhant and I'll be explaining the methodology section of this paper. So having understood the problems with existing method, let's now explore the
solution proposed by the authors of this paper, which is called T-Core. T-Core stands for Temporal Correspondence for Video Representation Learning. T-Core is specifically designed to solve the two main challenges in video representation learning. The first one is uncertainty in temporal sampling. The model struggles to learn effectively when frames are chosen randomly. And the second one is inefficient information compression. Existing methods are wasting resources on the pixel level details instead of learning the high level features. So the authors address these challenges with three main innovations. The first innovation is called sandwich sampling strategy. For each target frame, two auxiliary frames are selected, one from the past and one from the future. This provides the model with clear temporal guidance, reducing the uncertainty. The second module they called patch matching module. This module directly aligns the masked patches of the target frame with the two auxiliary frames. But instead of doing this in the pixel space, it works in the latent space, making it faster and more efficient. The third module or innovation they call is self-distillation framework. The model uses a teacher-student
setup where the student model learns from the stable teacher model. This teacher is updated using exponential moving average, providing consistent guidance. These three components allow T-Core to learn high quality video representation without suffering from the limitations of existing methods. Now let's discuss sandwich sampling strategy in detail. Well, this strategy gets its name because it sandwiches a current frame between two auxiliary frames, one from the past and one from the future. But how does it work? Well, a first current frame is selected from the video. Then two auxiliary frames are chosen. The past frame is chosen from a range of frames before the current frame, and the future frame is chosen from range of frames after the current frame. The selection of these frames is not random. Instead, it uses a technique called uniform sampling, which means the past and future frames are picked from a defined range. The range is determined by two parameters, alpha and beta, which ensures that the frames are not too close or not too far away from the current frame. These two These two auxiliary frames provide the model with temporal guidance, helping it understand how objects move or change. The benefit of this approach is that it avoids the uncertainty of random sampling, and the model always has clear temporal context. It knows what happened before and what could happen next. The patch matching module and self distillation framework will be explained by Devansh now.
All right. Next up, we have patch matching module, which is the second more relevant innovation in the T-core. So PMM is designed to help the model learn temporal correspondence. In simpler terms, it helps the model understand how objects in a current frame are connected to the object in the past and the future frames. And here how it works. First of all, we take the mask patches of the current frame, and these are treated as queries. So these are the part the model needs to learn about. Next, we use is auxiliary frame, which are a past frame, a VP, and VF, that is a future frame, and these are treated as dictionary, and this will be the source of possible answers. Next, model uses a cross attention block, which is a method of connecting the mask patches of the current frame to the most relevant patches in the auxiliary frames.
In simpler terms, we can say a model asks, where can I find a similar patch to this mask patch? And the future and the past frames provide the answer. Finally, the model uses a self-retention block to further refine these connections to ensure that the spatial structure of the mask patch is accurate. This helps the model to stay focused on the right areas of the frame. Uh, but why it is important? Because instead of trying to imagine what should be the mask region, the model can directly retrieve the information from auxiliary frames. And because this is done in a latent space, it focuses only on high-level features rather than focusing on small, low details like color, texture. It's more efficient as we do not need to process pixel level directly.
So the third innovation we have is the self-distillation framework. It's a way, it's a setup to train the model itself. The self-distillation is a method where the model learns from its own knowledge, becoming better and more stable over time. It uses a teacher and student setup where the student model, number one, is the one that actually learns during training, and the teacher model provides a consistent guidance. But here's the key: the teacher model is not trained directly. Instead, the teacher model is the exponential moving average of the student model. This means that over time, the teachers become a more stable and consistent version of the student. For each training step, the teacher weights are gradually updated. In simpler terms, we can say the teacher model become a collection of the best knowledge learned by the student model, but in a more stable form. Uh, the T-core uses three branch structure architecture that is. Number one, we have a student branch which learns from the input video. Number two, we have a teacher branch provides target and guidance to the student. Third, we have an auxiliary branch which uses that the PMM model we talked in the previous slide, align the temporal information from past to future. To further improve the stability of T-core, T-core also uses a technique called temporal squeezing. This prevents the model from depending too much either on the past or on the future, ensuring a balanced understanding. Together, these three components, sandwich sampling, PMM, and the self-distillation, make T-core a highly effective method for video representation learning.
Uh, Hi everyone, this is Priya and I'm going to explain about the T-core complete architecture. Okay, so let's start with the T-cores. So in normal method, frames are selected randomly from a video, which is often miss the connections between the motion and time. But in T-core, for each frame, there are extra two frame are selected. It's like one is past frame and current frame and future frame. Okay, so this selection is doing using uniform sampling. That means instead of picking one frame randomly from anywhere, the model picks from the fixed time range before and after the range is controlled using the values alpha and beta, that is parameter. Okay, so because of this, the model always see the frame is correct order, or clear the time gaps. It helps it learn how object moves and change over the time, solving the problem of uncertainty in the random frame selection. This strategy is called sandwich sampling, as it places the current frame between the past and the future frame like sandwich. Okay, so next is PMM processing. So that is patch making module. Okay, so when we mask some patches in the current frame, the model needs to figure out what those patches could be. So it treats the mask part as a query, like questions, and then it took into the past frame and past frame and future frame, which are used like dictionary of answers. So uh using core attentions plus self attentions. Like first using core attentions, the model tried to find the patches in the past and the future, okay, and that match the mask patches. Then self attention is applied, improve the quality of those match and make sure they are spatially accurate. All of this happen in the latent space, which means the model work on the future and the help model learn meaningful changes over the time instead of just low level details like color and textures. So PMM helps the model solve both problems, like it remove uncertainty and save computations times. So the next is teacher student learning. So like it explains how the model trains itself using methods called uh, distillations. Okay, so there are two models working together. First is the teacher-student model, and the second is the teacher model. Like first is student model. So student model is one being trained, and the teacher model gives the stable guidance, but the teacher is not trained separately. It is exponential moving average of the student. That means it slowly follow the students become more stable over the time. The model has three branches. First is student branches, second is teacher branches, and third is auxiliary branches. Okay, so the student branches learn from the video. The teacher branches gives the correct output match, and the auxiliary branches uses the patch matching modules to help with the temporal alignment. Also, one special things used is called temporal squeezing. So, which means the model learns not to rely much on either past or the future, but to balance with the whole setup is like fully self-supervised. So the model do not need any label data. It learns just watching the videos. So next, come to the database. So first model is pre-trained on the Kinematics 400. That is, it is a large database which is 2 lakh, like 2,40,000 videos clips showing four different 400 different human accents. Then no test how well the model performs. They used like UCF 101, which is over 13,000 model of sports and accents, and HDM B51, which has 67,000 plus videos with 51 accents type like something, and that one is something V2, which is also very detailed database, more than 2,20,000 approx clips showing fine-grained interactions like picking up something or moving something. The performance is measured using top 1 and top 5 accuracy for UCF and HMDB, yeah, HMDB, and mean average positions for the something database. So the next is experimental result. So The model used this experimental is based on the Bayesian transformer. Basically, the VIT-V and it's like it is basically the VIT-V and the VIT-L version. For the training, they use the ADAM-W optimizer and along with the cosine learning rate schedule, which gradually reduce the learning rate. Like a large portion of a frame, 75% of the patches was masked during the training. So the model learned to predict from the limited informations. The training was done for the 800 epoch using the 32 NVIDIA V100 GPUs that show how much uh, compute uh, compute power was used to train this powerful model. So overall, like T-Core model introduced a well-designed pipeline using smart frame selections. So um, like semantic patches matching and stable self-learning system to learn from the video without any label. So it performed well across the multiple database and solve the key problem in making it strong contribution in this area. Yeah, so that's all for thank you so much.
Hi everyone, my name is Pramesh Kumar. So I will be discussing the key advantages of a T-core model. The author of T-core have carefully designed it to overcome the two main problems we have discussed: uncertainty in temporal sampling and inefficient information compression. Here is a direct comparison. Compared to random sampling method, T-core uses sandwich sampling, which always provide the model with a clear temporal guidance, past and the future frames. Compared to the pixel space method, such as the MAE or video MAE, which focuses on the low level details, T-core learns in a latent space, focusing on the high level concept like objects, shapes, and action. Unlike other latent space method like Dino V2 or iBot, which may struggle with the temporal relationship, T-core uses the patch matching model, means PMM, to directly connect mask patches of the current frame with those in the past and future. Finally, while many models uses basic self-distillation, T-core uses a carefully designed three batch three branch structure combining the stability of the teacher student model with the temporal guidance of PMM. This perfect combination of technique makes T-core a powerful and efficient solution for the video representation and learning. And the further slide, I will be discussing about the conclusion of the T-core model. In the conclusion, we have concluded is temporal correspondence for the video representation learning represents a significant advancement in the self-supervised video understanding. The author of this paper have carefully tackled two critical problems that earlier we have discussed: uncertainty in a temporal sampling and inefficient information compression. So their approach combines three powerful techniques, that is sandwich sampling, which provides the temporal context using past and future frames. Second one is patch matching model, PMM, which efficiently aligned mask patches with the most relevant temporal information. And the third one is the self distillation framework, which ensures stable high quality learning using a teacher student model. As we have seen in the experimental result, T-core outperforms existing method across the various video tasks, making it powerful tool for the video representation learning. We hope this presentation have given you a clear understanding of this innovation method. Thank you for your time and attention. So thank you from our group side. The group number is 41. Thank you.